The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Next presentation is by Mr. David Springer, who is president of Davis Energy Group, and he's joining us from California to talk about radiant cooling in a hot, dry climate. Welcome, David.
Thank you, Steve, and thank you, Linda, for kind of getting me started here on. I could never explain exergy as well as you did. So Davis Energy Group is an engineering firm in Davis near Sacramento, California, and we do a lot of energy modeling. And we're also a Building America team member. Building America is a DOE-sponsored program. It's a residential program designed to help builders build homes more efficiently. And we lead one of 10 teams in the U.S. called the Alliance for Residential Building Innovation. So what does radiant cooling have to do with concrete? Well, I'm going to demonstrate how concrete slab foundation can be an integral component that reduces heating and cooling energy use and improves comfort and helps to achieve a zero net energy goal. In California, we have imperatives to reach zero net energy for new residential buildings by 2020 and commercial buildings by 2030. So everybody's kind of pushing to figure out how to do that. Also, to optimize electricity time of use, which is becoming an important thing. And as we start seeing alternative ways of producing electricity, we need to kind of balance those. We're taking a backward approach in that we're going to build it first and then model it. So I'm going to show you some information on houses that were actually built and then subsequently modeled. So what are the characteristics of an ideal comfort system? Linda already touched on a lot of this. Superior comfort, low energy use, the ability to zone your comfort, have a thermostat in each room, minimize use of space for ducts and equipment, that keeps architects happy, operate quietly, using inexpensive to maintain, of course, and utility friendly. Utilities like favorable load shapes that match what their supply is, and also demand response capability. So Linda already kind of covered this subject, but I'll just point out here that in the left case, we have forced air cooling with 78-degree thermostat set point. The floor temperature is 76 degrees. We have a mean radiant temperature of all surfaces averaged out at 80 degrees. And the operative temperature, the comfort you experience, is about 79 degrees. If you cool the floor to 70 degrees, take the same other conditions, and you have an operative temperature that's about 76.5. And these are just examples. So how do we improve equipment efficiency? Linda also kind of addressed this. One is correct sizing. We want equipment that's properly sized. We want distribution systems that are properly sized, so we don't have short cycling, we don't have excessive losses in the distribution system. And we want, of course, install high-efficiency equipment, and it has to be correctly installed. Refrigerator charge is correct and all that. And we want to reduce the thermal lift. And the thermal lift is this concept of exergy. The more you have to lift the temperature, lower the temperature, the more work you have to put into it, the more electrical energy you have to subsidize to achieve this level of comfort. And the graph there just illustrates what typical air conditioners, how they perform, where this lower curve here is a bunch of data points for a 13-SEER air conditioner operated in the California desert. And you can see that as the indoor-outdoor temperature difference increases, the EER of this 13-SEER equipment goes all the way down to almost 4. With a SEER 21 piece of equipment, the EER goes down to about 11 at higher temperatures. So the more work they have to do, the more energy it takes to do it, and lower the EER. EER is energy efficiency ratio in BTUs per watt hour of delivered energy. Some advantages of radiant distribution include improved comfort in all seasons, and I can attest to that. The top picture there is a picture of our house 12 years ago, and I wouldn't live in a house without radiant heating anymore. Anyone who you talk to who's lived in a house with radiant heating or cooling would not switch. They're very, very comfortable. It eliminates space required for ducting. They're easy to zone, quiet. You have a higher evaporator temperature for cooling, so you don't have to cool the water to as low a temperature for radiant distribution as you do for forced air distribution. And you can shift the load by storing energy in the slab, and I'll show how that's possible. So Linda already addressed the concept of active mass. I kind of think of it as bringing the mass alive. You're able to tap it. Normally, if you have passive mass, it might work well if you have a good diurnal temperature swing where it cools off at night. You can open up the house or the building, ventilate it, cool off the mass. But in climates like these desert climates, it doesn't cool off below 85, 90 degrees at night sometimes. So you really don't have an opportunity to get that passive cooling. We did a project with Walmart in Las Vegas where we used a cooling tower because the wet bulb temperatures are lower at night. We used a cooling tower to cool the water to run through the floor, and it can't handle all the load, but it could really offset the cooling load. Slab temperatures are generally more affected by ground heat exchanges and air temperature, but they both affect the temperature in the passive case, and the mass tends to moderate the indoor temperature, but doesn't really control it. With active mass, you can charge or discharge the mass at will to maintain the desired operative temperature, and you can charge it at times when it's more favorable to run the system. So, for example, in the wintertime, excuse me, you can run the system, say a heat pump system during the daytime when it's warmer to heat the slab. In the summertime, you can run that air conditioner or heat pump at nighttime when it's cooler, and you get a better exergy situation with milder outdoor temperatures and less thermal lift. So how do we make hot or chilled water? For residences, there's a couple of manufacturers of air-to-water heat pumps that are a lot cheaper than ground-coupled heat pumps. In our area, it costs about $2,000 a ton just for the ground loops. So it's kind of impractical. You can also use a condensing unit with a refrigerant to water heat exchanger. This is a picture of what I have in my house here, which is just a plate heat exchanger that substitutes for the indoor air coil and makes chilled water instead of cool air. For heating, air-to-water heat pump again works, and you can use a water heater as a heat source also. So, Building America is about research, and we have to kind of define our research questions before we tackle the research. And so these are some of our questions. What's the distribution efficiency of a radiant floor, and how does it compare to forced air? Are there any benefits on the efficiency side? How much can performance be improved by reducing that thermal lift? And is it possible to maintain comfort while operating equipment at optimal times of the day, like I was talking about, running, for example, a cooling system during the nighttime instead of during the daytime? And finally, something people are in this climate be interested in is what happens with condensation on the surface of the slab. Is that going to be a problem? And if so, how can we solve it? So there are 2 houses we monitored. We're actually monitoring 3 right now. The top one is in Borrego Springs area of California, and there were 5 houses actually built there with identical floor plans with different wall systems and different mechanical systems that we got to play with several years ago. And in this bottom one is a Tucson, Arizona house that we're currently monitoring. And you see also a figure here of the TRNSYS model that we applied to these houses. So the Dewpoint problem can be solved by taking the chilled water and running it through a coil before we send it to the floor. So we're removing moisture, and at the same time we're raising the water temperature a little bit so it's not cooling the floor as much. So we're doing some sensible cooling, but a lot of latent cooling with that fan coil, and then getting good thermal distribution, good comfort with the radiant system. And the fan coil can be small because humidity transfers very readily inside of the space. It tries to equalize the humidity, and so it doesn't really matter where you put that cooling coil to remove moisture. So these are some results from some of that Borrego Springs data. The top curve is a standard air conditioning system that had an average EER of 7.1. And the bottom curve is same exact condensing unit tied to a refrigerant to water heat exchanger. And in that case, we are running the water through a fan coil and through the floor. And there we had a 30%, more than a 30% increase in the EER, just by the fact that we had less thermal lift to do, and better comfort. This second house is in this Tucson house. We wanted, the mistake we made in the Borrego Springs house is we didn't insulate under the slab. And we thought that there wouldn't be that much heat transfer. If we insulated the perimeter slab, there wouldn't be that much heat transfer downward. We were wrong. So those great advantages we got in the EER, we gave away in terms of ground loss. So we decided, let's try it again with a well-insulated slab. And let's look at the relationship between EER and thermal lift, both on the water side and on the air side. And let's see if the fan coil is necessary in this climate to prevent condensation on the floor surface. And also, we wanted to test this cool and coast control strategy where we can cool the house at night, let it coast through the day, and then cool it again at night so we get less thermal lift out of the system. So the measured ground transfers using, we measured ground transfers using temperature sensors above and below the insulation. We knew the R value of insulation, therefore we can calculate the actual heat transfer. And we compared those results to calculated values for a typical ducted system for the same house using ASHRAE standard 152. For the radiant floor system measured, we got about 98% distribution efficiency. The Building America has this benchmark program, benchmark for residences. You can apply kind of standard protocol to any building. And there we got 65% distribution efficiency using this benchmark. And if we tightened up the ducts, we got that up to 78%. And if we put the ducts inside conditioned space, we got it up to 95%. So still not quite as good as we measured with the radiant floor. So this is what some of the data from this Tucson site looks like in terms of the impact of leaving water temperature from the heat pump on the EER. So we got a lot of data. It was very confusing. We said, how can we possibly make sense of this? So we separated it into temperature bins, separate outdoor temperature bins, 5-degree bins here. So you can see that there's a slope going the right direction here on all of these temperature bins, such that as the leading water temperature increases, the EER of the equipment increases. Next we looked at EER versus outdoor temperature, and that's very dramatic. And what's going on in these different symbols here is this is applying this cool and coast concept where we're cooling the house at night during the coolest times of the night and then carrying that through the day the next day. And these black symbols here are cases where we had constant set, or rather daytime or normal operation of the system to maintain comfort. We also found that we had higher EERs if we didn't use the fan coil. If we just simply cooled the floor and didn't try to cool the air, remove moisture from the air, we had higher EERs, primarily because of the fan energy use of the coil. So what about condensation? What we're looking at here, this green squiggly line is the surface temperature of the slab, and what we want is we never want to see the dew point temperature approach that green line, and the red line is the dew point temperature. So we had a pretty comfortable 15 degree or so comfort margin between, or safety margin between the dew point temperature and the temperature of the slab. And we see also of note here is the indoor temperature, which is this blue line here that kind of gets lost. That's how much the indoor temperature swings on a daily basis. And it's only about 3 degrees in this house, which is pretty tight. It's sit panel construction. So this is what the cool and coast looks like. What we're seeing on this part of the curve here is the heat pump operation. And we see that that's happening right around, centered around midnight when it's coolest outdoors. This black line is the outdoor temperature. The dotted green line is the indoor temperature. Again, it's only fluctuating by about 3 or 4 degrees. And we're seeing an average EER for a 13-SEER piece of equipment of over 13, which is unheard of. You just don't get that kind of performance out of residential 13-SEER air conditioners. So it worked. So TRNSYS modeling, air-to-water heat pumps aren't included in DO2 or Energy Plus models, and there's very limited capability for modeling radiant heating and cooling with those models. And so we worked with TESS, who they sort of manage TRNSYS, to develop models using performance maps from manufacturers to see how close we could match our actual data. And the preliminary results show that TRNSYS has at least similar trends to the monitored results, and we see a crossover at about 70 degrees. So this purple line is the TRNSYS curve fit of the TRNSYS data, and this is the actual data. So we've got a little work to do to get better calibration of the TRNSYS model. We've found that models are pretty good usually at predicting changes in performance, but not very good at predicting absolute performance. So looking at just TRNSYS modeling results, with this mixed mode delivery with a fan coil and radiant floor, in this case, we modeled an annual energy use of 2493 kilowatt hours. If we cut out the fan coil, it's down to 1703. With a cool and coast in a mixed mode delivery, it was 2330. With radiant floor only, we got it down to 1408. So 17% savings combining the cool and coast with radiant floor. And these results generally support the trends that we see in the monitored data. But as I said, we need to do more calibration. The slopes of the performance curves are a little different. The indoor temperature response to forced air cooling seems to be too rapid in the models, and the model shows higher heat pump energy use in mixed mode, even though we have higher water temperatures entering the slab, which should improve performance more than we're seeing. So in summary, radiant cooling offers a definite way to substantially improve system efficiencies, especially in dry climates. We don't know yet. We need to do more research to see what we can do in wet climates as far as using the fan coil to remove moisture. If you insulate the buildings well enough, that this cool and coast concept works pretty well. That if they're tight buildings, then the daily temperature swing is minimized, and you don't have to worry too much about comfort issues. The evaporator temperature, on the evaporator temperature side of things, we see about a 6% per 5-degree increase in entering water temperature improvement in EER. And of course, again, on the on the outdoor air side is much more extreme. In the house that we tested, the fan coil wasn't needed to avoid the risk of condensation, even during the monsoon season, when that area gets pretty heavy moisture from the monsoons, and we didn't see any problems with condensation during that period of time. And the only problem with radiant cooling is it limits the use of floor coverings, and also if you have a two-story building, it's a little tough to put the slab on the upper story. And if you did, and you had a cold slab, you could attract moisture into the wood structure supporting the slab. So it really is kind of limited to single-story construction. However, you could put a fan coil on the second floor, and that's what I did on my house. I've got radiant floor heating on the first floor and the fan coil taking care of the second floor. We need more air source heat pump product offerings, and we need better controls. Those are two stumbling blocks we ran into in our projects. So, any questions?
What about setting thermostat temperatures? What are they? Does the operator have to know to offset?
Well, the builder in that Tucson house is occupying the house, so we have a way to easily test different thermostat strategies, which we've been doing. And so using just a typical setback thermostat, we've been able to play with different strategies like this cool and coast approach versus just a fixed set point versus other strategies.
Thank you.